Bo Han from NTHU, and he will talk about FRB.
Is it working? Yes. Okay. Hi everyone, I'm Oliver from National Tsinghua University. Today I would like to share a result using machine learning to discover the hidden repeating fast radial bursts. So it is a work using machine learning, and we know that one day the machine will rise and take over our world. So in case that happens, I put the AI's lens here in case one day I'm accused by them that's ignoring their contribution. So first, let me start from a problem we are trying to solve here. We know that the FRBs could be classified as repeaters and non-repeaters. For the repeaters, it repeats, so our observation can detect it for several times, like we're showing in this GIF file. But if it is a non-repeater, then our telescope only detects it once, and never see it happens again. So we call it a non-repeater. This classification seems simple, but it might imply a different origins of the FRBs. For example, some hypothesis says the FRBs might originate from a pulsar. If it is the case, then it is possible that the FRB is repeating, because pulsar itself is periodically detected by us. So it is probably a case of repeater. But some other hypothesis says the FRB might originate from the merger of neutron stars. In this case, the merging of the neutron star is a catastrophic event, and it only happens once. In this case, the FRB is very unlikely to repeat because the merge only happens for a moment. Okay. So, our conclusion so far is classifying repeating and non-repeating fast radial bursts is important as there are given the different physical mechanics driven by it. So we know this problem is important, but here we have another question. We know that a repeating FRB is definitely a repeater, correct? It is trivial. But if it is a non-repeater, then now we have a question. We see it is non-repeating is probably just because we are observing it for a short time. And if we extend the observation period for longer, if we keep looking at it for 3 days, for 3 years, for 3 centuries, then probably one day we will see its bursts one more time. I'm showing here, we detect it now. Okay, so we know it is probably a non-repeater because we are not seeing its burst anymore. But if we wait and looking at it and wait, then one day we will see it burst another time. It is supposed to burst. Oh yes, okay, good. Okay. So the major questions of our research is it possible to use other technique rather than the expensive monitoring to detect this kind of repeaters? And in this research, we answered, yes, we have found a solution to figure out this problem. Okay. The way we use this, the way we address these questions is using machine learning. To apply the machine learning, we need data first. So we collect the FRB samples from child FRB catalog. In this catalog, there are more than 500 FRB samples. For each sample, we have certain physical parameters here. So 500 samples, and each sample 13 parameters. Mathematically, it is equivalent to 500 points in a 13-dimensional space, well, mathematically. So it is like a lot of points in a high-dimensional space. And now what we want is to project these complicated dots onto a 2D plane. To put it on a 2D plane, it is more easy for a human to understand the structure behind the data. And the way we are doing this is using machine learning model. So what is the machine learning contributing in our work is to do this projection from a high dimensional space to a 2D dimensional projection. Okay. Eventually, our projection results in a plane look like this. So this plane, this figure, is the major result of our work. In this figure, the repeating FRBs are colored in green and pink. Here, green and pink. And for the rest of them, colored in gray are the non-repeaters. Okay. In this figure, we see that the color points, which means the FRB repeaters, are concentrated in these three clusters. Right? So these three clusters are most important results of our research. And meanwhile, we see that there are quite a few gray points here, are mixing with them. Here and here. So we perform a clustering algorithm. On this end, we pick those gray points in these three clusters and identify them as our repeater candidates. As it means that if the projection points are similar, they are all concentrated in these three clusters, then that means they are actually having similar physical properties. These non-repeaters have similar physical properties with those FRB repeaters here. So we are coloring this FRB, well, the original non-repeaters in blue, and we now call it a repeater candidates, as they are very close to those confirmed repeaters. Okay, so it is important. They are the candidates we found in this research. So initially, in the China FRB catalog, only 93 repeaters are there, and the rest of them, 474 FRBs, are non-repeaters. But now, in my research, there are 188 non-repeaters are now classified as the repeater candidates. And this means that we have increased the fraction of FRB repeaters for 3 times. Okay, so it is a much larger portion. Okay. So now, our machine has already successfully accomplished our goal to find the repeaters. But now here induce another question. What has the machine found in our data? What did the machine rely on to do this classification? We want to know the clue in the data. So in order to answer this question, we perform an analysis of the feature importance, which means the importance ranking of the certain parameters here. Then we found that the 2 most important parameters are the highest frequencies of the data and the peak frequency of the data. The FRB's frequencies are the most important points. Actually, if the most important factors are frequencies, then it is implying the spectral shape of the FRB. Okay, so the spectral shape is important. So to better understand this phenomenon, we have plotted all the FRBs on a plane of highest frequency versus the peak frequencies. Okay. In this figure, the repeaters, including candidates, are now plotted in red, and the non-repeaters are plotted in blue. Okay. Clearly, we see there is a border here that is classifying the repeaters and non-repeaters. So it is how the machine relies on to do this classification. Okay, so I think this is the most important clue here. But we should still understand that this border is not clear enough for human to understand or to figure out. We cannot just, if there is no colors, then actually we cannot understand the border here. Okay. So we still need machine to do this work for us. Okay, so let me finally summarize the conclusions. We have successfully using unsupervised machine learning to classify the hidden repeated fast radio bursts. And our machine has classified 188 FRB candidates from the 474 original non-repeaters. So 40% of the original non-repeaters are actually the contaminated samples. And if our result is correct, then we have tripled the fractions of repeater samples. Okay. Finally, we have a follow-up observation program using fast telescope is going to verify these results. So these are the most important conclusions of my work. This work has been already published. So if you are interested in the details of this work, you're welcome to utilize this QR code to access the paper. Thank you very much.
I have one small question. I want to know whether it is possible to improve your work because we just classify whether some repeaters are some potential repeaters. I don't know whether maybe in the future you can predict the time scale of those potential repeater can have another burst again. Yeah, because for the non-repeaters, I suppose that you already know the time scale of the repeat of its best radio burst. So for the potential repeaters, can you predict the time scale of the next FRB?
Oh, I think this is.
That's what I mean for the input of your work.
Okay.
Is it possible? Or because now you only have 5,000 samples, so maybe you may not have enough sample to do such kind of survey.
Well, this is a very good question, but sadly, I think this is almost not possible in our cases because the repeater in our samples has the original, the confirmed observed repeaters has only 93. And among them, because for each repeaters, they might have several bursts. So if we are trying to evaluate periods of bursting, then we need those FRBs that has already burst so many times. But this kind of FRB actually has a much smaller portion in our data. So if we want to evaluate the period, then I think we need at least 10 or 100 times more data to accomplish the problem value you are saying. Yes, but if in the future, especially we already have fast telescope now, well, focusing on the observation of FRB, I think this work is possible, but in the tri-FRB case, I think it is hard.
Yes, in my personal opinion, if you can find a period, then you can know those potential repeaters that you predict whether they will have the next burst, and you can control whether your prediction is right or not. Yeah, that's my personal opinion.
Thank you.
Do you find different DM distribution for the repeater candidates and non-repeaters? The dispersion measure.
The dispersion measure, well, if I remember correctly, the dispersion measure is not included in our work. So it is hard to answer these questions. Is dispersion measure matters?
I would really be interested in seeing just a histogram of dispersion measures for your repeater candidates versus non-repeaters.
Okay, I just recall that actually during our research we have plotted dispersion measure, but it is almost randomly distributed among these plots. So,
Okay, thanks.
I have a quick question, a comment on that. So basically, dispersion measure, we may expect the difference between non-repeating and repeating, but it highly depends on the mental shift distribution of these two populations. Therefore, as he said, that when we plot the histograms, probably we don't need to see the significant difference.
Okay, interesting. Thanks.
Thanks for the interesting talk. And since the sample size is not very large, I'm curious, will the size of training set affect the results?
well, the training sample,
Will the size of the training set affect the results?
well, the size of the training sample affect the results. If you are asking if we have more samples, will the results be better? Well, I think this is not the case in this research. But if in machine learning and we are amplifying the training samples to improve the results, then that is more likely to happen in the optimization type problem. But in this case, we are doing machine learning with clustering concepts. And in clustering, it only focuses on the similarity between the samples. So if we increase the training samples, then that we may just see that each cluster here are becoming bigger and more clumping. So I think increasing the training sample might not help.
Okay, thank you.
Last question, Chicken. So, 2 or 3 pages before, that is our friend. Yeah, then that one, next one. Next one, yes. There is a, there are only 3 one of repeater in the right hand view, in the right hand side, in the non-repeating one. Can you comment this question? This repeating FRB in the region.
Oh, you mean the repeater FRBs are located here?
And in that, yes.
Okay.
Comment this to their home?
Well, actually, this is, we'll consider it as the errors induced from the machine learning. But of course, if the points are not there, then it is perfect. But sadly, our research has also included some errors at these clusters. So we cannot say that this result is 100% perfect. But we know that most of the repeaters are concentrated in the left-hand side. Okay, so it is error.
So let's speak again.